What up? It's time for day 9 of Advent of Code. I have a few different solutions with different optimizations to show you today. They tell us for part 1 that we meet an amphipod and he's trying to make more contiguous free space by compacting all of his files, but his program isn't working. And so he shows us his disk map, which is a list of numbers. And the disk map uses a dense format to represent the layout of files and free space on the disk. The digits alternate between indicating the length of a file and the length of a free space. So for example, this list of numbers will indicate that there's a 1 block file followed by 2 blocks of free space, and then a 3 block file, 4 blocks of free space, 5 block file. They also tell us that each file on disk also has an ID number based on the ordering of the files as they appear before they are rearranged, starting with ID 0. So for example, again, the file with 1 block would have file ID 0, 3 blocks would have file ID 1, 5 blocks would have file ID 2. And so they tell us that the amphipod would like to move file blocks one at a time from the end of the disk to the leftmost free space block until there are no gaps remaining between file blocks. So you can sort of see in this picture that we move all the 2's over into the empty spaces. Or on this bigger example, we basically push all the numbers on the right over to the left to fill up all the free space. Then the last step that they tell us is to calculate a checksum, which is the sum of multiplying each of these blocks' positions with the file ID number it contains, and starting with the leftmost position being position 0. They tell us that if a block contains free space that we should skip it. So for example, for this one, we would say 0 times 0 plus 1 times 0 plus 2 times 9 plus 3 times 9 and so on, all the way till we get up to here, in which case we can stop. And the question they ask us is, what is the resulting file system checksum after moving all the files as the amphipod wanted? Let's look at our input, save it. So getting our input for today is going to be pretty easy. Since our input is just a big list of numbers representing our disk map, we can read out the entire file and then just make sure that we cast all of the numbers in the file to ints. So that's what I'm going to do, right? I'm going to say disk equals tuple, because we want a collection of numbers rather than a string. And I'm going to cast each of the numbers in the file into ints. And then to get the whole file, I'm just going to read the entire file. I'm also going to make sure to get rid of any white space that might be at the end. And this should do what we expect, right? If I print disk and I return, I get a bunch of numbers. So for part 1, how do we approach it? What we can do is we can keep track of which block we're on with an index. We can have a start block and an end block, or a left block and a right block. And we'll fill up our space with the numbers on the right and go on as we go on from the left. So one thing you might notice looking at this example is that all of the original blocks from the left don't move, right? Like 0, 0, 1, 1, 1, 2, and so on. Because the space between them gets filled quickly, they don't end up moving. The only ones that end up moving are the later ones that get moved to an earlier position. Point being that we can keep track of where we are on the left and right sides, and we can fill our file up from the left side until we encounter empty space, and then once we encounter empty space, we continue from where we were on the right side and fill it up with values until the left and right sides meet, right? So here I would fill up 2 zeros. I encounter 3 empty spaces. So I fill it up with 3 values from the right. Now these numbers are here and I need to include them in my file. I encounter 3 more empty spaces and I continue from where I was on the right. I keep doing this until the left and right sides meet. Let's try coding it up. So now to implement part 1, I'm going to say define part 1, and it's going to accept disk. And so I'm going to print part 1 of disk. So now if we remember the format of the disk map, they told us that each of the even indices indicated file sizes, and then all the odd indices indicated empty blocks in the disk map. So let's sort of just pull those out, right? I'm going to say the files are the disks at the even indices, So I'm going to start at 0 and then go for every 2. And then the empties are going to be almost exactly the same, except I is going to start at 1. And so now I have my blocks which correspond to files and my blocks which correspond to empty spaces in the disk map. And now that I have files and empty by themselves, you might notice that the indices of the files list actually correspond to the file IDs that they talked about in the problem description, right? Like if you remember, it says each file on disk has an ID number based on the order of the files as they appeared before they are rearranged, starting with ID 0. So file 0 is going to correspond to file ID 0 here. And so whichever indices we keep track of in files are the indices that we can use in our checksum. So I'm going to make sure to start at 0 and end it at the end. So 0 and length of files minus 1. And not only are these keeping track of our files, but they're actually our file IDs. So for each file, starting from the left, I'm going to add all the file IDs and then I'm going to add the empty space afterwards. So to keep track of our new disk, I'm going to just make an empty list. And then I'm going to add all the file IDs from the blocks at start. So I'll say new disk.extend. And I want to include my file ID, which is just start. And I want to include it however many blocks are indicated at file start, many times. So the multiplication symbol will take this list and make it and repeat the element that many times in the list. And then it'll basically concatenate that list to the end of new disk. And once I've added all the blocks from start, I want to make sure to increment start by 1. And so in this case, if start is greater than or equal to end, then I want to make sure I add whatever's at the end. So I want to go here and change this to end and change this to end. And this will just make sure that if the left and right pointers meet, that I don't miss those last few elements that were in the end block because I break out. And then I'll just return, I'll just break out, right? Now otherwise, if it's not greater than or equal to end, that means that there's going to be empty space afterwards I should fill up with numbers from the end. So what I'll do is I'll iterate through each of the empty positions and then I'll fill it up with numbers from the end until I run out of numbers from the end or I run out of empty positions, right? So I'm going to say for underscore in range empty. And which empty do I want? I want the one that corresponds to the start, the file I just had, which was at start. See, so I incremented start by 1. I should subtract by 1 to get the one that we originally had. And this is the empty that immediately follows the file that we just added to the new disk. And for each empty space, I want to make sure I have file IDs remaining in my file blocks from the right. And so if I don't, I want to move to the previous block. Like if we look over here, I want to fill this empty space up with 9s until I run out of 9s, and then I move on to 8s. And then when I run out of 8s, I move on to 7s and so on. What I'll say is while the file at the end doesn't have any more digits for me to put, I'm going to subtract 1 from the end. And so this will allow me to move from the 9s to the 8s or from the 8s to the 7s when I need to. And so once I know that I have an element to add, I'll say new disk.append end, because that's the file ID of the file. And then I'll make sure to indicate that I used one of the ends from this block, right? So I'll say files at end minus equals 1. That way, once I run out, it'll decrement end. And so now that I've done this, I should have my new disk filled with all the values like the amphipod wanted. And so I should just be able to say I want to return the sum of the file IDs, so the index, times the actual value, right, for I and val, and enumerate new disk. And so if we print this out, we get this large number right here. And this was the correct answer for part 1. Let's look at the problem description for part 2. So for part 2, they tell us that he'd like to try compacting the files on his disk by moving whole files instead. So this time, we should attempt to move whole files to the leftmost span of free space blocks that could fit the file. And we should attempt to move each file exactly once in order of decreasing file ID number. And if there's no span of free space to the left of a file that is large enough to fit the file, then the file doesn't move, right? So now we should look at this whole block of 9s and try to move this whole block of 9s over. And then look at this whole block of 8s and we notice, oh man, there isn't a space large enough to move the block of 8s. So the block of 8s just stays there. Then for these 3 7s, there's a space with 3 spaces right here. So we can put this block of 7s in and move it away from here and so on. And this is what our final state ends up looking like. And the file system checksum is the same, right? We're still going to say 0 times 0, 0 times 1, 9 times 2, and so on. And we're going to ignore these empty spots. So here's what I did for part 2. For part 2, what I noticed was that each of the initial chunks that they give us, so these blocks, so there are blocks that belong to a file and there are blocks that belong to empty space. These chunks never change size, because if they did, that would mean that the file didn't fit in the initially given block, which is not according to the problem description, right? And so what I did was I kept track of which files were at which blocks, right? So initially in the first block there's a 0, in the second block there isn't anything, in the third block there's file ID 1, and so on, right? And then to fulfill the amphipod's wishes, what I did was I iterated through the file IDs in decreasing order, and I moved them to the chunk that could accommodate them. And I kept track of the filled up space in the remaining space. And so each chunk got a list of file IDs which it was holding. So maybe this chunk right here initially wasn't holding anything, but then once it encountered 9, now this chunk with the 3 spaces is holding file ID 9, and there's still one more space. And later, the 2 ends up coming here. So this chunk is holding both file ID 9 and file ID 2. And so what I want to do to know which chunk gets what file ID is just iterate through these file IDs in decreasing order and find the earliest chunk which is large enough to accommodate it, and then put it in accordingly. So let's implement that. So for part 2, we want to say, look, let's think of our disk as being composed of chunks. And so what is our disk really? It's our chunk size of each of our chunks. And so initially I want to say, hey, which file ID is at which chunk? Each chunk is going to get a list of file IDs which represents which file IDs are at that chunk. And so initially I'm going to start them all out as empty. We know that each of the files initially have themselves at their chunk, right? So I'm going to say for file ID chunk in enumerate range of 0 length disk 2, because remember they're only at the even indices. I want to say at chunk of chunk equals file ID, and that's going to be the only element in the list, so I'm going to just assign it like that. But I could also say append. And there's going to be some useful values that we want to keep track of here, right? Like I might want to ask, hey, for a given file ID, which chunk is it in? Or I might want to say, for a given chunk, how full is it, right? And so I'm going to keep track of that with dictionaries. I'm going to say filled equals a dictionary, and I'm also going to say chunk of is a dictionary. So chunk of is going to say I'm going to give it a file ID, and it'll give me back a chunk. And so here I can say, hey, look, the chunk of file ID should be chunk, and filled of chunk should be chunk size of chunk. One more thing I might want to know for a given file ID is what the size of the corresponding file is, right? So I'm going to say the file size is another dictionary that I want to keep track of, right? And file size of file ID is just going to equal the chunk size of the chunk. And we don't have to worry about the empty ones because the empty ones don't have any file information and they're not full. And we should make sure that we initialize filled with a sensible default because we might want to get the fill value of an empty chunk. And sensible default in this case is just 0, right? So we can use default dict or we can use counter. I'm going to use counter. It's basically a dictionary that initializes with 0 if the key isn't there. And so now that we have our @chunk and our sort of helper dictionaries initialized, let's do the process of iterating through each of the file IDs in reverse order and seeing if there's a space large enough to move it to. And we want to make sure that we take the earliest of those possible spaces, right? So to actually get the file IDs, well, we know that we just got all the file IDs in the file size. So let's just iterate through file size backwards. And so then for each of these file IDs, what we want to do, we want to look for a chunk which comes before it and take the earliest one which is big enough. And if it's not big enough, we'll just continue because that means that the file should stay where it is. But if not, we should swap the current position of that file for the position that we found and update all of our helpers accordingly. So I'm going to look at each chunk in the range of chunk of the file ID because we never want to actually get to or past the file ID that we're trying to move up. And I'm going to calculate the space, which is the size of the chunk minus how filled it is. So I'm going to say the chunk size of the chunk minus filled of chunk. And if that space is large enough to accommodate our file, then we should break because that means that we found a big enough chunk. And if we get through all of our candidate chunks and we don't break, that means we didn't find a sufficiently large space and we should just continue. But in the case where we don't continue, we should update our @chunk and our filled. So since we're moving the file away from its current chunk, we should remove it from its @chunk list, right? So we should say @chunk of the current file ID should have the current file ID removed. And in all of these cases, that should basically just mean popping it from the tail. So you could also just pop. For the chunk that we just found that can accommodate the file, we should append the new file ID. As for filled, we should do something similar, right? We should say filled of the chunk of the file ID that we just moved away. We should subtract the size of it, right? We should say file size of file ID is subtracted from it. And why do we do that? Because we just took the file away from the chunk and put it into the new candidate position. And then we should also update how filled the chunk that we just moved the file to is. Since we just moved the file there, we should add the size of the file to that space, right? And you could also update the chunk of each file, but it ends up being not relevant to our computation, so I'm going to leave it. So now we can fill up our new disk with all of the file IDs from each chunk. So I'm going to iterate through all of my chunks by iterating through the length of the disk. And then for each file ID at each chunk, I'm going to extend it similarly to part 1, right? So I'm going to say new disk dot extend file ID times file size of file ID. And then I also need to make sure that if there's unfilled space that I include that, right? So I'm going to count my unfilled space by taking the chunk size of the chunk and subtracting how much of it was filled. And so unfilled might be 0, but that's fine. I'll say new disk dot extend 0 times unfilled. And so if unfilled is 0, this list will be empty and we essentially concatenate nothing to the disk and move on. But if there were unfilled spaces, we'll make sure to append that many zeros and then they'll get left out of our sum that we take, right? And then our sum is going to be exactly the same as it was up here. And so now if I run this, I should get this number right here, which was exactly the answer for part 2. Nice. You might have noticed when I ran that it came about pretty slowly. So can we make it faster? Whenever we're looking at performance, we should benchmark our functions so that we can track improvements. I'm going to make a decorator called bench, and what it's going to do is it's going to take in a function, and it's going to return a function which behaves exactly like the original, but it's going to time it and then print the time to the console. Bench is going to take in a function, and it's going to define a new function, and it's going to take in whatever arguments and keyword arguments the original one did, and it's going to keep track of start time. It's going to get the result from F with all the appropriate args and keyword arguments, and then it's going to print the end time minus the start time, and then it will return the result. So now we can just return our new F, or really maybe I should name that timed F, but whatever. And we're going to add that to each of our parts. And now when I run, we get a time for each part. To make this a little prettier, maybe we'll add some context, right? Maybe we'll say print part 1 and print part 2, naive, just like that. And now when it runs, we get part 1, a time, and a result. So where is this time sync actually happening? Where can we probably save the most time? If we take a look at part 2, we notice that there's a part where we do a search. We search for the earliest occurrence of a space large enough to accommodate our file ID with the size of file ID. So we might notice right here that we're doing this linear search, and we might ask ourselves, what's the easiest way to describe what this linear search is? Well, we're trying to find the earliest index, which is greater than or equal to a given number. This is the most expensive operation in our function because almost everything else is constant time except for this sum. But this sum kind of had to happen. It's about the size of the file. Can we speed this up? This operation can actually be optimized with something called a segment tree. What is a segment tree? A segment tree is a data structure that allows us to perform range queries like sums or maximums on a given array, and allows us to make updates to the array and to do both efficiently. And when I say efficiently, I mean log n time. How do we achieve this? Well, let's brainstorm a little bit. If I had this list of numbers, maybe this represents a list, right? I might want to know the sum from here to here, or here to here, or here to here, and so on. Your head might tell you, hey, let's use prefix sums. But I might also want to be able to update numbers in my array. And if I use prefix sums, then when I update, I'll have to redo the whole prefix sum array. So is there a way that I can efficiently get some queries, or max queries in our case, and do updates? And yes, there is. What we can do is we can partition the array into halves and then keep track of the query that we care about for each of the halves until we only get to maybe a single element or 2 elements, right? So each of these partitions will get smaller and smaller until maybe here each of these only contain a single number. And so this is what it shows in the picture, right? We have a list with 4 elements, and so we split it into 2 lists of 0 to 2 and indices 3 to 4, and then 0 to 1 and 2 to 2 and 3 to 3 and 4 to 4, all the way until we get to each array only having a single element in it. And then we can use this tree to either find sums or maximums in log n time, or to update in log n time. And so I have an implementation that I made over here. We can take a peek at. Here's our segment tree. It takes in a list of elements. It takes in a key. And so the key is basically what you would normally think of it as in Python. The key maps each of the elements to a number that you want the segment tree to use instead of the element itself. So you usually do that when you're working with indices. And then I also place in a binary operator so that there's some flexibility, right? The segment tree has the ability to keep track of sums or maximums and so on. And so I just made that something that you could pass in rather than hard coding it in, right? One thing we might ask ourselves is, how do we actually store this in memory? We could use a bunch of nodes, right? But a lot of times this is implemented with an array because you can simply represent the tree in memory as an array. And you can use multiplication to represent left and right. So usually you represent left with 2 times your current node and right with 2 times your current node plus 1. And you might ask, hey, how do we know what length the array should be? If we look back at our tree, we notice that in the worst case, it will be full, right? Like it'll have 1 node here and 2 here and 4 here and 8 here. And if we add all of those up, it'll never exceed 4 times the original length of the input array. So we can use that as a upper bound for our implementation. So if we look at our implementation, we see that our tree representation is just an array of numbers, which is 4 times longer than the length of the input elements. And so when I build my tree, all I do is, if I have a subarrays of size 1, I just insert that element into the tree, and I make sure to apply my key function. And otherwise, I look at my left and my right, and I build each half accordingly, making sure to use my binary operation after I've built each half to keep track of the current node. And then getting the queries or updating can each happen in log n time, right? So how expensive is this build operation? Well, it only gets called on the order of the length of this list, and so it's O of n. As for each query, basically I can say, hey, from index L to index R in my array, what is the maximum or the sum, whichever one I passed in. Basically, if my range in terms of where I'm at in the tree is equal to where I want to be for my indices, I return the value of the tree at that node. Otherwise, I traverse the tree by narrowing accordingly and then applying my operation. And so I will never have to traverse more than the height of the tree, and so this operation will only be log n. And something similar can be said for the update, right? When I want to insert a value, I need to just make sure I update each partition which contains the value, which corresponds to a path going from the root to a leaf in my tree. And so I never need to do more than log n updates. For our specific operation that we're interested in, which is getting the first index, which is greater than or equal to a given element, we have to put the stipulation that it's a max segment tree. So I made this separate one here. And the reason we have to make the stipulation is because we have to check pretty explicitly if the number is less versus just using the binary operation. But so what do we do here? Here I specify the range I want to look through and the number. And because the number of recursive calls I'll make is on the order of the height of the tree, this operation will only be log n, which means that this segment tree can help us to achieve a faster part 2. If we can replace this linear search with one using the segment tree, then we can achieve a speed up. So let's try it out, right? Once we've initialized all these values for each of the chunks, we should manage the chunks with the segment tree. So basically what we should say is we should say our max tree is equal to the max segment tree of what? Well, I'm just going to use the indices of my chunk size array, or any of the arrays that correspond to all of the chunks, right? So I'm going to say range of length of disk could work even, right? And what do I want it to actually be keeping track of? Well, I want it to be keeping track of the space. That's what we're querying, right? It says if space is greater than or equal to file size of file ID, then break, right? So then I need it to take in a chunk and calculate this space. So that's going to be my key function, right? I'm going to move this space up here, and instead of it being a variable, now it's going to be a function that takes in a chunk and returns how much space is left at that chunk, right? So I'm going to say key equals space. And so now we have a tree which keeps track of our space that we can query for spaces like we wanted, and we can update when we need to, right? So here, instead of doing this linear search, I can just say chunk equals max tree of get first. And what do I want to get the first of? I want to get the first index, which is greater than or equal to file size of file ID. That's what the line down there says, right? Right here. And I want to make sure that I don't look past chunk of file ID. So I'm going to make sure I bring this over here. And I think I'll include a -1 because I think it's inclusive, right? And then when I do these updates, I want to make sure I also update my max tree, right? Because I'm changing how much space is available at the chunk that I selected. So what I'll do is I'll say maxtree.update, and I'll say, hey, just update this with the new value at chunk, right? And do the same thing for the chunk of the file ID. And so why am I just saying update chunk with chunk and update chunk of file ID with chunk of file ID? And the reason is because I use this key function, right? Key equals space. So what this is going to do, this is going to take the position at chunk and it's going to update it with space of chunk. I just need to tell it to do so explicitly, but it's going to do it under the hood, right? If I wasn't using a key function, I might say update the position at chunk with space of chunk. Otherwise, everything should be about the same, right? We did the exact same query, and so we should be able to fill up the disk the same and calculate our checksum. Let's compare the time. And so we see we get the same answer, but we get it about 25 times faster. Now, you might ask, Jaden, do I really have to write a whole segment tree just to use it in the competition? Isn't that a lot? And one, I would say, I'll post this online. You can use this as a template. But two, there is another solution that we could use, and this is courtesy of my friend Abdel, which uses something from the sorted containers library called SortedList. And that you can just import. And so what does that solution look like, right? Let's try it out. So here I use segtree, which is a good general data structure. But in this case, there's something that we can take advantage of. We know that the size will never exceed 9 because each chunk was represented with the size digit from 0 to 9. So instead of using this very general segment tree, what we could do is we could simply look through each size and keep track of which indices are available for that size. So I'm not going to write this one. I'm going to just show Abdel's code because it's not mine anyway. I sort of rewrote it a bit just to make it a little bit easier to understand, right? Because he uses single letter variable names. But so if we look at this part to sorted list, we see that he has a list that's called unfilled with size, and it's basically just a bunch of uninitialized sorted lists. And so he takes all of the empty chunks and he adds them to the array. He says, look, all of the empty chunks that are of size 3, here's all their indices. All the empty chunks of size 5, here are all their indices, and so on. And what sorted list allows you to do is to just see what the smallest one or the largest one is in log time. And it also allows you to add or remove the elements in log time. And so he just looks explicitly at every size. He just says, look, for size and range, file I to 10. So for the size I'm looking for, or bigger, if you can find an unfilled space, which is that big and has an index less than the one I currently have, then choose that one. And then he does something similar where he discards the space, fills it up, and then he updates it with the new unfilled space, right? So if, let's say he found a space that was size 5 and the file was size 3, he'll put it in there, and now he has a new unfilled space of size 2. And so he'll make sure to add that back so that it can be used for another file down the line. The other thing that was confusing with his solution that took me quite a while was this. What is going on with the list accumulate file? Well, it's giving us the positions from this sum. Well, first of all, what does accumulate do? What accumulate does is if I have a array, it'll give me the sum as I go. It calculates the prefix sum, so accumulate will give me something that looks like this: 1, 3, 8, 15, right? And he saves this in a list. But why do we want this? Well, what my friend noticed is that if we have a disk, that taking that sum tells us what the position is in the checksum at the given index, right? So, for example, let's say I've passed through these 3 chunks. Well, in my checksum, I'll have to look at position 0 for the first file, and then I'll add 2 zeros, so 1 and 2 for the empty space, and then 3, 4, 5 for the second file, and now I'm at position 6, which is exactly the sum of these numbers. So basically, he found a way to quickly find what the starting position is for a given chunk by caching it in this accumulate array. But so how is he using it? What is going on in this total? What is this monster term that we're adding to total? Well, so what do we know? We know that we're at chunk J. Chunk J is the chunk that we're moving the file I to. We also know the file ID, and we know the size of the file, which is file I. And so normally what we would do is we would just say, let's multiply the file ID by the position, which starts at position at J, and we'll add 1 to the position until we run out of file IDs to add, which would be file I number of times, right? So I might say total plus equals file ID times position at J, and then I might say file ID times position at J plus 1, and these are all terms I add to total, right? And I'll say total plus equals this, and total plus equals this, and I might keep doing this all the way until I get to file I minus 1. So I'm gonna put like a dot 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 here, right? Let's make sure not to forget the position at J. But so this might be what we might think of normally adding, right? We have file ID times the position, and then the next position, then the next position, all the way until we've exhausted the entire file. And so we could use a for loop to do this, but you might notice, hey, this sum is pretty regular. Maybe I could just put it into a term. So I might factor this part. Look, we have file ID times position at J. How many times does that show up? Well, we have 0, 1, 2, 3, 4, all the way up to file I minus 1. So it shows up file I times. So hey, that's what this part of it is. What's the other part? Well, I have a sum. The sum is 0 plus 1 plus 2 all the way up to file I minus 1. This is a Gauss sum, right? This is a sum that we can do with this formula right here, n times n minus 1 all over 2. Gives us the sum of 1 plus 2 plus 3 plus all the way up to n minus 1. And so if we factor this out, right, what do we get? We get this term. And so you might see a little bit more clearly now where this larger expression comes from. I'll leave that to you. But so if we try this function as well, we get our fastest time yet, which is about 4 times faster than my implementation. Thanks for watching. This one was a bit of a headache. I think it would be a better format to sort of go over the data structure in more detail rather than in the context of advent of code. So let me know if you'd like to see me showing how to use segment tree or how to implement segment tree and sorted list in a separate video. If that's something you'd want to watch, I'll make sure to post my implementation on GitHub and put the link in the description. And if you want to do leak code with me every day, I post in my Discord server in the description down below as well. And yeah, if you want to see more videos like this, please like and subscribe, and have a good one.